Hello, my name is Beomyeol Jeon, a PhD student at the University of Illinois, Urbana-Champaign, working with Professor Indranil Gupta. Today, I'm going to talk about Baechi, fast device placement of machine learning graphs. Baechi means placement in Korean. This work is done when all authors were at the University of Illinois. What we are really doing is placing machine learning models in seconds, but as effectively as expert placement. As machine learning has shown its potential, ML models are getting bigger and bigger to achieve better performance. This plot shows the number of layers and number of parameters of language models from November 2017 to now. The ML community has been developing deeper models. Along with that, the number of parameters has been increasing exponentially. More layers and parameters made ML model graph size bigger. However, mostly commonly used accelerator GPUs do not have sufficient memory to train this model. This table shows all GPU models in AWS, Google Cloud, and Azure, and their memory size ranging from 8GB to 32GB. Even the largest 32GB GPU cannot run any models with 1.3 billion parameters. Recently, ML training has been run on devices such as smartphones, UAVs, drones, and so on. These devices have much less memory than GPUs. To overcome this issue, a natural choice is to use multiple GPUs. To feed on GPUs, a ML model graph is split into small subgraphs, and the subgraphs are placed on the multiple GPUs, for example, based on the topological order. This method is called model parallelism. Then, a question left is how to split and place operators in a graph on GPUs. Why does device placement matter? ML training is iteratively updating model parameters for each data mini batch. Each iteration is called a training step. The elapsed time for a single training step is called a step time. If the ML operators are placed badly, the step time increases because of the increased communication overhead and not exploiting parallelism well. Let's assume that we place operators well. However, if the placement time is very long, the entire training time will increase. For instance, let's say the ML training time itself is reduced by 2 hours due to good placement. But if generating this placement takes 10 hours, there's no gain by using this good placement. So, our goal is twofold. We need to place an ML model fast and well. There have been approaches to solve this device placement problem. The first one is placement by experts. This approach, however, requires domain knowledge and also needs significant manual effort. Another approach that gained attention today is using reinforcement learning, such as colloq-RL, hierarchical RL, and Plaistow. But very long time is required to place models from 2 hours and even 3 days. Another issue is that the RL model should be retrained when target ML model or deployment configuration changes. In this paper, we return back to our roots and apply algorithmic approaches to the placement problem. We present Baechi, a ML placement system that incorporates algorithmic approaches into TensorFlow. Our contributions are twofold. First, we propose 3 competing placement algorithms. We adapt parallel job scheduling and propose 2 memory-constrained algorithms called METF and MSCT. We also present a strawman based on topological order called mTopo. For MSCT, we prove that its generated placement is within a constant factor of the optimal under certain conditions. Next contribution is proposing optimization techniques that are necessary for efficient performance. With these, our Baechi system achieves both goals as mentioned before. Baechi generates the placement about 700 to 206,000 times faster than the learning-based approaches. In our evaluation, a model is placed on 4 GPUs within only 1.2 seconds. Also, the placed model shows only up to 6.2% higher step time than the expert placement. Next, I'll present how our placement algorithms work. The first algorithm is based on the earliest task first algorithm called ETF. ETF schedules an operator with the earliest schedulable time on its corresponding device first, and repeat this for the rest of the operators. The original ETF assumes there is sufficient memory to schedule tasks on any devices. This is an example graph that has 4 vertices representing operators. The numbers on a vertex shows compute cost and its memory requirement that is inside the parentheses. The numbers along with the edges represent communication cost. With ETF, the example graph is placed as follows. We modify the original ETF to consider device memory in scheduling. The modified algorithm follows the original algorithms but excludes the devices with insufficient memory in scheduling. The modified algorithm finds feasible placement with a slight increase of execution time. The next proposed algorithm is based on the small communication time called Sct algorithm. The Sct algorithm works similarly to ETF, but the key difference is to find the operator's favorite child among its successors and prioritize its scheduling on the same device as its parent. Intuitively, the favorite child is a successor that is most beneficial to be collocated with an operator. The favorite child is determined by solving an optimization problem to minimize execution time via ILP. In the example graph, let's assume that operator 2 is the favorite child of operator 3. Then, the placement by Sct would be like this, and this achieves shorter execution time than ETF. Like the algorithm before, we modify Sct by considering device placement. We apply LP relaxation for choosing favorite child. When the original Sct phases out of memory, MSCT successfully finds feasible placement with a slight increase of execution time. In the paper, we proved that MSCT is within a constant factor of the optimal under certain conditions. Now, we have placement algorithms for memory-constrained environment, and we have wonderful proof for MSCT generating the placement closer to the optimal within a constant factor. We implemented these on top of TensorFlow. Do the algorithms work well for TensorFlow? Guess what? First, we observed that the generated placement were rejected by TensorFlow runtime. We analyzed that and fixed the issue, but the performance was awful. The placement model step time was much higher than the expert placement. Also, the placement generation was not that fast. After thorough analysis, we identified 4 challenges. We need to deal with TensorFlow collocation requirement, excessive communication overhead, the massive number of ML operators, and the different network architecture assumed by the algorithms in the real environment. After addressing them all, we were able to achieve both fast placement time and good placement result as mentioned before. The first challenge is that the TensorFlow requires some operators to be placed on the same device due to shared memory space. This is a simplified TensorFlow graph for linear regression. In this graph, TensorFlow requires operators with same color to be collocated. Our algorithm do not consider this requirement, so the algorithm places such operators on different devices, and this placement is rejected by the TensorFlow runtime. To fix this issue, we first adjusted the placement that ignores this requirement. We tried various criteria to move all operators to the device where compute-dominant operator, memory-dominant operator, or a majority of operators are placed. Does this work? What we observe is inconsistent performance gain. Instead, we use co-adjust placement that considers this co-location requirement while scheduling. Particularly, when placing the first operator in a co-location group, we place other operators in the group on the same device. With this approach, we can get consistent performance improvement. The next challenge is blown-up communication overheads. When you split a model across multiple devices, inevitable communication overhead is introduced. Let's see this example graph that transposes the input tensor with the given permutation and reshapes it. Note that permutation and shape operators have very cheap computation cost. Since Sct assumes small communication overhead, it tries to exploit parallelism as much as possible. So MSCT places the input, permutation, and shape operators on different devices like this. This introduces data transfers, and their communication overhead is much higher than computation costs of perm and shape operators. This increases the step time. To avoid too much communication, we apply a mechanism called operator co-placement. If the operator's output is only used by its successor, we place them together. With this method, we can remove data transfers and achieve faster step time. Along with this, we also co-place respectively matched forward and backward operators together. This is a commonly used technique and very beneficial. The third challenge is dealing with the massive number of operators in an ML graph, since this increases the placement time. For example, 4-layer GNMT has around 22K operators. Generating a placement plan for this takes around 7 minutes. To minimize the placement time, we fuse operators that are directly connected and in the same co-placement group. This operator fusion looks similar to the existing operator fusion technique, but this is different. This fusion is to minimize the number of operators to schedule and place, whereas existing one is to improve the placed operator performance. When we apply this fusion to the linear regression example, the output graph changes like this. Do you notice any problem in this graph? This fusion generates a cycle. Since the proposed algorithms only work for DAG, this cycle generation should be avoided. We first tried to check all cycles, but that was expensive and not scalable. So we decided to use a conservative but scalable heuristic. Although this misses some fusion opportunities, the cycle generation is perfectly avoided. We observed that this fusion also helps achieve faster step time. To manage the massive number of operators further, we use forward operator-based placement. With sufficient memory, we can place operators by only scheduling forward operators, and then schedule backward operators to the devices where the corresponding forward operators are placed. With these techniques, we reduce the number of operators for 4-layer GNMT from 22K to 700 and placement time for 7 minutes to only 1.2 seconds. The last challenge is to deal with different network architecture assumed in the algorithms and in the real environment. I'm skipping this for brevity. This is the workflow of our Baechi system that works modularly with TensorFlow. The system receives TensorFlow graph and applies the optimizations. The execution simulator schedules and places the optimized graph based on the user-specified algorithm. Then it generates the placed graph and feeds it into the TensorFlow runtime. We evaluate our algorithm for inception V3 and GNMT on our local machine with 4 NVIDIA RTX 2080 GPUs connected via shared PCI bus. We first run experiment to answer this question. How long does it take to generate placement? We compare the placement time of MSCT, which has the longest placement time among our algorithms, with the reported numbers for 2 learning-based approaches. For placing inception V3, hierarchical RL takes about 12 hours. Placed takes around 2 hours. On the other hand, our Baechi system only takes up to 10 seconds. This is around 700 to 43,000 times faster than the learning-based approaches. For NMT model, hierarchical RL takes about 2 days. Placed takes around 3 days. Baechi finishes the placement only within 50 seconds. This is about 3,000 to 206,000 times faster than the learning-based approaches. Next, we measure step times of the placed ML model to see how well our system places them. We compare the expert's placement step time with ours. Low step time means the actual ML training will be faster. First, mTopo generated the placement that have up to 34% higher step time than the expert's ones. METF's placement shows -4.5 to 6.2% speed up. MSCT's placement shows -6.2 to 1.9% speed up. The previous step times are when the memory is sufficient to train an entire model on a single GPU. What if the memory is constrained? To answer this, we limit each device memory up to 30% of the total. The left table shows step times and slowdown compared to the sufficient memory cases. The right bar plot shows each GPU peak memory for the placed models with 100% and 30% of memory normalized to the 30% memory limit. In this case, ML models do not fit a single GPU. With the expert's placement, inception V3 is out of memory. GNMT is successful with a little slowdown. Baechi finds feasible placement with all proposed algorithms. With MSCT, the slowdown compared to the sufficient memory case is only up to 13.8%. The last evaluation is to see optimization benefits. After all optimizations are applied, the number of operators are reduced by 96.8 to 99.8%. The placement time shows around 76 to 230 times speed up, and the step time shows around 1.1 to 3 times speed up. Here are takeaways. We present Baechi, our first ML placement system based on algorithmic approaches. Our evaluation results show that Baechi achieves about 700 to 206,000 times faster placement time than the learning-based approaches. Baechi also plays well by showing only up to 6.2% higher step time than the expert placement. This concludes my talk, and thanks for watching.